Hi guys, next we're going to go over the 6.5 worksheet answers. Again, if you have questions, circle them. We can meet on Google Meet sometime this week to go over those questions live. So for number 1A, H2O has stronger IMFs than CH4. So CH4 only has London dispersion forces. H2O has hydrogen bonding and London dispersion forces. So the delta H of vaporization is higher for H2O than CH4. Part B, we have pH3 has London dispersion forces and dipole-dipole. NH3 has London dispersion forces and hydrogen bonding, stronger IMFs. So our hydrogen bonding is a stronger type of dipole-dipole IMF, so NH3 is going to have those stronger IMFs. So since the strengths of IMFs are different, the delta H of vaporization will also be different. NH3 should be slightly higher. 1C, both substances only experience London dispersion forces, but C3H8 is longer and has more electrons, so it has a larger dispersion force, making the delta H of vaporization different for the two substances. And part D, BH3 only has London dispersion forces. Remember, boron is one of the exceptions to the octet rule when it comes to Lewis structures. He is fine just having 3 bonds or 6 electrons associated with him. So there's only 3 bonds there. OF2 has London dispersion forces and dipole-dipole forces. So OF2 is going to have a bent shape like water does. And there's a very polar, well, slightly polar, I should say, bond between oxygen and fluorine. The IMFs are different, so the delta H of vaporization will be different. Number 2, answer should be that the heat absorbed during the phase change is used to break IMFs, allowing particles to separate from one another. 3A, I have, what's the question? Sorry, I did these last week. During what period of time, there we go, was the substance at its normal freezing point? That was between 1.3 minutes and 3.1 minutes. You might have rounded differently based on your estimation of the graph. Part B, over what period of time was the substance boiling? About 4.5 minutes to 7 minutes. Again, based on your interpretation of the graph, might have been a little bit different. Part C, what is happening in substances between the 1 and 1.5 minute marks? Particles are all in the solid phase, but the average kinetic energy of particles is increasing as heat is added to the system. Part D, what's happening to the substance between 2 and 3 minute marks? IMFs are weakening. The substance is changing from a solid phase to a liquid phase. The average kinetic energy remains the same, so there is no temperature change, but there is a phase change. In part E, between the 3.5 and 4.5 minute marks, particles are all in the liquid phase. The average kinetic energy is increasing as heat is added to the system. And part F, between the 5 and 7 marks, IMFs are weakening, substance is changing from a liquid to a gas, and the average kinetic energy of particles remains the same because, again, there is a phase change. For 4A, it says create a visual representation to show the interactions between particles in both samples during vaporization. So for 4A, I have these 2 images drawn. This is it's all backwards. This is dipole-dipole interactions basically here, and on this side we have ionic compounds. So here we would have IMFs breaking during vaporization, those dotted lines, and here we would have the actual bonds being broken during vaporization. B, explain why the vapor pressure of HBr is higher than the vapor pressure of KBr at negative 92 degrees Celsius. So KBr is held together by ionic bonds, which are much stronger than the dipole-dipole IMFs between H and Br. HBr molecules, I should say. Because IMFs are weaker, HBr has a higher vapor pressure than potassium bromide at the same temperature, as particles can more easily enter the gas phase. So if it's easier to break those forces holding particles together, then the vapor pressure is higher. For 5A, how much heat is required to melt 12.5 moles of pure sample of ice at 0 degrees Celsius? It's 75.1 kilojoules for the answer. Part B, how much heat is released when 12.5 mole pure sample of water freezes. 75.1 kilojoules are released. 6, part A, how much heat is required to vaporize 22 mole pure sample of water at 100 degrees Celsius? Should be 902 kilojoules. And part B, how much heat is released when 22 pure sample of water condenses at 100 degrees? It would be 902 kilojoules released. Part 7, how much heat is required to melt 12.6 grams of 24 karat gold at 298 Kelvin? The melting temperature of 24 karat gold is 1063 degrees Celsius. The molar heat capacity of 24 karat gold is 25.6 joules per mole Kelvin, and the heat of fusion for 24 karat gold is 12.5 kilojoules per mole. So this is one where you have to consider the phase diagram where temperature is increasing, how much energy that takes, and then during the melting phase, how much energy that takes to melt all of that sample. So overall, you should get 2.5 kilojoules. I got that by adding together 0.8 kilojoules and 1.7 kilojoules. Okay. So those are the answers to the 6.5 worksheet. If you have questions, mark them and then ask me. I'll make another Google form so we can select what problems we need to go over when we meet for Google Meets. Have a great day.